Great. Good morning, everyone. I'm Michael Pfeiffer, and today I'm going to be talking about stressors, what they are, where they come from, and how to stop them from hurting products. Just as a kind of sort of something to keep people to keep in mind, this is a 45-minute presentation, so I'm not going to be going into certain areas in great detail. That's all I can cover. Like, so discussions about corrosion, fatigue, and wear, just covering a couple slides. Please keep that gentle reminder in mind. I have courses that go into more detail, and lots of other people have lots of courses that go into a lot of detail about those, but I have a limited amount of time to talk about those. Just a brief background about myself. I have a bachelor's and master's in metallurgical engineering and a PhD in material science and engineering. And I have over 25 years experience working with companies to help them with metals engineering. I help with product design, that's with material selection, and also sometimes even the engineering the form of a component. Also manufacturing process development, quality improvement, failure analysis, and root cause analysis. And then I also offer metallurgy training design engineers, quality engineers, and manufacturing engineers. We have on-demand courses, webinars, and on-site training. And if you need to reach me after this, my contact information is on the second slide, and you have the slide deck. And I think, and Fred, you posted the slide deck will be available to people.
Yes, that's right. It'll be, I mean, I just sent out the link to it, which they can download, but it'll also be on the recording pages that we put up on Ascenda.
So I'm going to talk about the products, components, joints, and reliability, stressors that act on components and joints, some different degradation mechanisms for materials, sources of stressors, and then evaluating the effects of stressors. So first, I want to take a high-level view of product design. So as I said earlier, I'm a metallurgical engineer, and myself and also all the people that are materials engineers come at product design from a different perspective than mechanical engineers and other people that are involved in product design. So I wanted to cover that quickly. So I see any product as being an assembly of components and joints. And actually, I see a product as being an assembly of different materials that have been manipulated in different ways to get different components and joints that are used in a product. And engineering the components and the joints in a product is critical in order to meet the performance, reliability, and cost requirements of a product. And today I'll be talking about things that affect the reliability of the product and some of the considerations that go into designing components and joints for reliability. So this shows a bicycle, and these are the different components that make up the crank assembly in the bicycle. And for joints, I'm referring to non-mechanical joints between components. This would be weld joints, solder joints, and adhesive joints. So when I think about reliability, I'm thinking about how materials in a product can degrade due to exposure to the use conditions. So steel screws will corrode when exposed to water. Some plastics become brittle when they're exposed to sunlight. Coatings on surfaces wear away. And if there's too much degradation of the component or joint, then it stops functioning as required. And that can lead to one or more product functions no longer meeting specifications. So in if it's a shaft in a piece of equipment, then if that shaft breaks or fractures during use, then the whole piece of equipment can shut down. If it's an important resistor in a piece of electronics, then the entire electronics can shut down. So component performance, reliability, and cost depend on two things. It depends on the form of a component and joint, that is its shape, its dimensions, and its features, and it depends on the materials, the alloy. So I'm going to talk about metals, but there's also the same concepts apply to polymers and ceramics. But for metals, it would be the alloy, the method of fabricating a component, heat treatment that's used on the metal coating. Those are just some of the things that can go on in the designing a component. And we can engineer both the form and the metals in order to optimize the design to meet performance and reliability requirements at the lowest possible cost. And so in order to do this, we want to make trade-offs between materials and form in order to optimize the design. As a materials engineer, what I see is that in a lot of cases, the focus is more on the form. People pick the form and then force the materials to fit the form, rather than saying that the form, that it's open to discussion, picking an initial form and then looking at what materials are available and looking at what trade-offs can be made to come up with a component or joint that has good reliability and performance, but also is at the lowest possible cost using materials that are readily available. And then engineering, metals engineering means applying the science of metals to engineering decisions and problems, and the same thing would be true for polymers and ceramics. So that's it for my for just helping you understand my perspective to product design. Before I go on, can you type into the chat box? Just, I know we have a number of people attending. What's your background? Are you design engineers, manufacturing engineers, quality engineers, reliability engineers? You just type that into the chat box. Okay, great. We've got a lot of reliability engineers, a few design engineers. Okay, so a lot of reliability engineers and a few mechanical design engineers. Okay, so that's great, and I think that hopefully my perspective will be informative to you. All right, so now I'll talk about stressors. So stressors are the conditions to which a component or a joint is exposed to during handling, shipping, and product use. And stressors fall under the categories shown here. I mean, mechanical, thermal, chemical, electrochemical, radiation, and electrical. So mechanical, and this list is not meant to be exhaustive, for the subcategories, but it includes static, dynamic, or cyclic loads, impact, and rubbing that can cause wear. Thermal would be elevated temperatures or low temperatures. Chemicals would be gases, solvents, acids, or bases. Electrochemical means materials exposed to a corrosive environment. Radiation includes UV lighting, sunlight, radiation from power plants, and electrical includes voltage and current. And there can also be a combination. So you may have hot gas, so it'd be an elevated temperature combined with a corrosive gas. So that is it for the discussion, the overview of the different types of stressors. So when we're designing components and joints, we need to think about what the stressors that components and joints are exposed to, and then design the components and joints so that they don't fail during use. So now I'm going to talk about material degradation mechanisms. So the most common degradation mechanisms are shown here. It includes corrosion, fatigue, wear, creep. Also, property changes that occur during exposure includes embrittlement, loss of strength, color change. And I also put on here electromigration. I know a lot of you are involved in electronics probably, and I know that electromigration can be a problem for electronics. So I'll have some quick slides to talk about these different degradation mechanisms. So corrosion is an electrochemical reaction between the material, so typically with metals, in the reaction with oxygen, fluorine, chlorine, acids, bases, or water. So this shows, the image shows, or the diagram shows a piece of zinc, and it's in contact with hydrochloric acid. And in the hydrochloric acid, there are chloride ions and hydrogen ions. And at this part of the zinc, there is an oxidation reaction occurs where zinc atoms lose two electrons, and zinc ions are created. And those electrons move through the zinc, and they react they react with the hydrogen to form hydrogen gas. So this is an oxidation reaction. This is a reduction reaction. So corrosion involves chemical changes of the metal and the environment. And it also involves electrical charges that are flowing from the metal to the environment. And the general equation for the oxidation reaction is shown here. And then here are a couple examples for a couple different metals. And the reaction involves the loss of electrons from the corroding metal atom, and some atom in the environment gains an electron. And so, oops, this atom is supposed to go here. I don't know why it didn't, but in any case, so the corroding atom becomes a positively charged ion. So that is, and then there are several different forms of corrosion. You can read these on your own, but many of you are probably familiar with them all, especially galvanic corrosion, people trying to design and select materials so that galvanic corrosion doesn't occur. All right, so that's it for corrosion. The next is fatigue. Fatigue refers to the progressive, localized, and permanent damage that arises from repeated stressing or straining. So this graph shows a stress versus time. You see repeated cycling between a high and a low stress. Now, sometimes the stresses are not as periodic as this and don't look as nice as this. They can be sometimes very erratic, such as with vibration for an automobile going down the road. But in any case, it's a cyclic stress. This repeated stress or strain results in crack formation and growth. And the thing that's interesting about fatigue is that this occurs even though the average or nominal stress on the component is less than the metal's yield strength. So when we see a fatigue failure, we have a fracture surface that has all or part of it showing no plastic deformation, because on a grand scale, the stress on the material is less than the metal's yield strength. There are 3 requirements for fatigue to occur. There has to be a cyclic stress or strain. A portion of the stress has to be tensile in nature, and the localized stress has to exceed the metal's yield strength. And this is possible when there are stress concentrations on a metal. And stress concentrations includes notches or changes in cross section or even surface roughness that can result in an increased level of stress at a local point compared to the stress over the entire piece of metal. There are 3 stages of fatigue failure. There's crack initiation, where microcracks form, and then they grow and coalesce to form larger cracks. So the microcracks are forming at the surface, and then these cracks grow and they coalesce to form the larger crack. And then with continued cycling between the high and the low stress, the crack continues to grow. And then finally, there's fracture. So as the crack continues to grow, the amount of material for which that's still intact is decreasing, or the cross section of metal that's still intact is decreasing. So as a result, the stress on the remaining intact material is increasing because less of the material is supporting the applied load. And as the crack continues to grow, the stress on the intact material continues to increase until the stress on the intact material is large enough that the crack shoots through the rest of the material and the part fractures. The point at which that happens depends on the size of the crack and the fracture toughness of the material, which I'm not going to get into. There are different sources of stress, can include the surface load, which can be tensile, bending, shear, or torsional. Differential thermal expansion between 2 components that are mated together. that results in stresses being applied to, tensile stresses being applied to one of the metals. So for example, in this case, during heating, if this part has a higher thermal coefficient of thermal expansion than this part, then this material at the higher temperature, this material will be under tensile stresses. And then during vibration, such as a car going down a road. All right, so that's it for fatigue. Then there's wear. Wear is due to the friction between surfaces, and the friction results in material removal. And there's a number of different wear mechanisms. I'm just going to talk about a few of them. But the wear is a result of rolling, sliding, and impact between two metal surfaces, and it can also be due to impingement on a surface of particles and fluids onto the surface of a material. This shows adhesive wear, where there is local welding between two metals, and when the surfaces move apart, the one metal pulls material away from the other material. And this is adhesive wear, and this can result in loss of material from this metal, the metal that's having material pulled away. Then there's abrasive wear, where it's actual gouging of the material or pulling out of the material between a hard metal or a hard material and a softer material. And then there's fatigue wear, which is repeated rubbing of surfaces, and the stresses between the surfaces result in cracks being generated at on one or both of the surfaces. And the final mechanism I'll discuss is fretting. Fretting wear. Fretting wear is a problem with, like, in electrical connectors, and it's a result of micro motions between two materials, and those micro motions results in wear of that material. And then, so in this case, is a brass in contact with a tin plated material, and the wearing results in the tin wearing down, and tin debris being created, and that tin oxidizes. Also, the tin coating on this material also oxidizes. And if enough of the wear debris builds up, it can become, it can impact the electrical conductivity between the two metals that are being mated. All right, so that's it for wear. Then there's creep. Creep is the time-dependent deformation at elevated temperatures. So this is a fancy way of saying that at elevated temperatures, a material can start to undergo plastic deformation at loads that are less than the metal's yield strength, at least the yield strength at room temperature. So this graph shows strain versus time for a metal undergoing creep, and the metal is elongating over time due to exposure to the applied load. For metals, creep starts to occur between 1/3 to 1/5 of the melting point temperature, and this is shown in degrees Kelvin. Creep also occurs in polymers. It's also time-dependent deformation, and creep can even occur at room temperature for some polymers. And environment degradation can also hasten creep. So exposure to UV, ultraviolet light, solvents, and water can hasten the creep. Then there are property changes that occur to a metal due to its exposure to the environment, and these changes that occur then result in degradation of the properties. And the changes that occur are occurring to the microstructure. So in metals, it would be a change in the phases that are present, or something that's causing embrittling of the material. And in polymers, it would be changes in the molecular in the way that the molecules are linked together within the polymer, or it can even alter the molecules. So in metals, elevated temperatures can lead to formation or the growth of an embrittling phase within the metal, and that can lead to loss of ductility, or cracking and fracture at stresses less than the metal's yield strength. In polymers, UV from the sun and acids and organic solvents can break up the molecules or alter the molecules, and resulting in loss of ductility, cracking and fracture at stresses less than the material's yield strength. It can also result in reduction of strength and a change in appearance of the material. All right, so that's it for the very quick discussion about the different degradation mechanisms. So now I can start talking about sources of stressors, and then I'll finally talk about evaluating the effects of stressors. Someone has a question. Someone's asking, can I discuss the stages of creep? Yeah, I don't have time. I don't have enough time to talk about that now. We could, if you want, maybe if you want to email me, we can talk about it afterwards. So now I'll talk about the sources of stressors. So there are five general sources of stressors. First is the functionality of the component or joint. There's a use environment, interactions with other components and joints, minor abuse, and misuse. So the first one is sources of stressors. It would be the first one is source I'll discuss is the functionality. So these are stresses related to the purpose of the component or joint. So in the case of the bicycle frame and the weld joints, the frame and the weld joints are meant to support the mechanical loads of the rider riding on the bicycle. So there's specific loads on the welds and on the tubing that are associated with the functioning of the bicycle. In the case of a skillet over a fire or over a heat source, the pan of the skillet is meant to be exposed to heat in order to heat up so we can cook something. And in the case of an electronic circuit, there's current and voltage flowing through the circuit, and that's related to the functionality of the circuit. So you can look at, and I guess another caveat for this discussion is it's impossible to cover the millions of different applications and the different functionality of different components. So I just have a few for examples, but you can imagine for the different components you're working with, thinking through what the functionality is for that component and the stressors on the component or joint. Then there's the use environment. What is the environment in which the component or joint is being used in? So we're concerned about the temperature of the environment, the chemicals, the gases, any radiation, and bodily fluids if it's something that goes inside of a human body. So the temperature, like things that are used, components that are exposed to a blast furnace. So there might be like this pole this guy is using. This pole is meant to support mechanical loads, but it also has to be able to withstand the temperatures that it's being exposed to by the blast furnace. And there's plastics that are exposed to UV radiation. If they're certain plastics will become embrittled due to exposure to the UV radiation. That's not the primary functionality of the plastic piping, but that's what happens. And then finally, things exposed to a seashore environment. So metals will corrode. Metals such as in buildings will corrode when exposed to the seashore. Anyone remember a recent event that occurred? It was about a year or two ago, involving a failure near the seashore. Right, the condo collapse, and that is due to the rebar in the material the rebar corroding and pushing the concrete out. So that's the use environment. And when thinking about use environment, for more complicated products, we have to think about the environmental stressors and how they may vary depending on their location within the product. So if we're looking at an automobile, the same would be for a truck. The environmental conditions in the engine compartment are much different than the environmental conditions in the passenger compartment, and they're different than the environmental conditions in the exhaust area. So we have to think about the differences between these environments and the stressors associated with that. Then there's interactions with other components. So components that are in contact can be the cause of other components wearing, or be the cause of fatigue or corrosion. So in the case of gears, we can have wear between the materials that are in the gears. If there are two components that are mated together, or if it's a joint, such as a solder joint in electronics, we have to be concerned about the thermal expansion between the materials. If the product or if the materials will see changes in temperature, and if the materials have different coefficients of thermal expansion, and because this can result in fatigue of one or both of the parts as they expand and contract during the heating and cooling. And then for materials that are in contact, we can have, or two metals in contact, there can be crevice corrosion, which occurs in gaps between components, and galvanic corrosion when two dissimilar metals are mated up against each other. And then for components that are not in contact, you can have outgassing from one component, let's say from a polymer or a rubber material, and that outgassing influences or causes degradation of something else in the that's in the same environment as that thing that's outgassing, or if some component is giving off like UV light or radiation, and other components are exposed to that. So these are interactions with other components and joints within the product. And then there's minor abuse. So this is normal, reasonable mishandling, such as someone dropping a phone or a car going over potholes. And you probably have, for your products, have different minor abuse that you test for, because it's expected that people are going to do things, not handle things properly while they're using them, but it's expected that they'd be handled in, they'd be this handling is expected. And then finally, there's misuse. These are stressors that far exceed the typical use conditions. We don't consider these in the design requirements when coming up with design requirements. There is a reasonable outer limit to what we can expect our products to be able to withstand. So for someone, I'm sure a lot of people here have probably heard experiences of people who have dropped their phones in the toilet. And then it's not good to drive your car in lots of water or through deep water, especially deep salty water. So those are examples of misuse. So we're focusing on really not on thinking about misuse, but on the other four. Though I think from time to time, we're made to reconsider what is misuse and should it really be typical or should it be considered minor abuse? And then for the final part of the section, I want to talk a little bit about identifying stressors. So I went through pretty quickly the different stressors, and then where they can arise within where they can arise or how they arise for a component or joint. But as part of our responsibility is trying to figure out or identify the stressors, and then design components and joints that can withstand the stressors, so that the products don't fail during their normal expected life, or at least if they do fail, they don't fail catastrophically. So so I want to talk a little bit about the identifying stressors in the product design process. So this is a general high level view of the design process. So thinking about a product, first step is to identify the product requirements, come up with the form of a prototype for the product. Then if there are sub-assemblies within that product, identify the sub-assemblies and the sub-assembly requirements. And then based on that, identify the components and their form and their requirements. And then with this information, and these requirements include performance requirements, reliability requirements, cost, manufacturing, sustainability, and some other things. Based on these requirements, it's then possible to take the next steps by identifying the materials selection criteria that can be used for the components and joints, and identifying candidate materials and evaluating them. In order to get to this point, though, we need to have good information about the product and about the sub-assembly requirements in terms of reliability. How is this product being used, and what's expected? What's the expected reliability of that product, and what are the different components going to be exposed to? So getting this information as soon as possible during a product design is critical in order to be able to make these decisions and do this work. So we need thorough and accurate information as soon as possible. So for identifying stressors, there are some different paths for getting the information we need about the stressors. If you're a company, if you're a tier 1 company and you're working doing a project for an OEM, let's say you're designing a sub-assembly for an OEM, or maybe even designing the product for the OEM, or you're doing a work for a government project, then you're going to depend on the design requirements document from your customer. And hopefully it spells out the reliability requirements and the stressors that you have to be concerned about. If it doesn't, then you have to go back and nag the customer about this information to get this information. There's also industry standards, SAE, IPC, Underwriters Laboratories, NEMA, and a host of others that have standards regarding different products and how to design the products, and also reliability concerns and reliability testing for those products. There's also government regulations. And then finally, there's internal reviews amongst engineers at a company. And during those reviews, it should include design engineers and materials engineers and reliability engineers, and talking about the components and joints in the product and understanding how the components and joints are being used, and use a failure modes effects analysis to understand and try to put numbers to the stressors to which the material will be exposed to, or the components will be exposed to. So there's a lot of engineering that might have to go into coming up with and identifying all of the stressors. And then if you're an OEM, then you rely on industry standards and government regulations for the reliability requirements for the product. And you also can have internal reviews and doing FMEAs in order to identify the stressors on the components and joints, on the product, sub-assemblies, and components and joints. Have a brief example. I worked on a project. It was an electronic module that was going to be immersed in transmission fluid. And the requirements document from the customer was missing the information about the chemistry of the fluid that was going to be in contact with the module. And there's a problem with this because you can see there's an electrical connector here, and these are these connections go into the module. And the concern about the fluid was that how aggressive was that fluid going to be, and do we have to be concerned about it attacking the sealant material between the connectors and the shroud? And the client or the OEM was not very forthcoming with that information, and it was leading us down the path of having to use a really expensive sealant material. The material was $1 a gram versus something that was a little bit less expensive. And that price point was very difficult for this project. We finally found out what the fluid was going to be but it took a lot of time. And as a result, but during all that time, we had to spend time and money pursuing different paths. Have any of you ever been involved in projects where the reliability information was not forthcoming and you're just trying to guess at testing or designs for the product? Well, that's good. So the one person says oftentimes they want me to determine the reliability after the design is done. That's frustrating. And at least, and the problem with that is then you're going to have test failures and having to repeat tests, which then delays product launches. All right, great. All right, so you can commiserate with what I'm saying here. Good. All right, so the final thing I want to talk about is evaluating the effects of stressors. Since a lot of you are reliability engineers, you'll be familiar with, I think you'll be familiar with what I'll be talking about. So in order to evaluate the reliability of products and components, we want to do reliability testing to evaluate the effects of the stressors. So we're exposing the materials to the stressors and evaluating the response. So we're looking at evaluating the type and amount of degradation, the composition of the material, the microstructure, the mass, and also looking at the effects on the properties and performance. And then also, if it's a product, you're looking at whether the product works as it's supposed to. I like taking the approach of trying to do testing to evaluate components and joints on the material level rather than having to build up an entire product, so that I can evaluate it, so that by the time I'm built up the entire product, I have enough information to have some confidence that the product is going to pass testing the first time, or at least have fewer problems during testing. So there's product testing, and then there's materials level testing. So with product testing, the test sample is the entire product, and we're evaluating the product performance versus exposure to the use conditions. So temperature, salt spray, thermal cycling between a low and a high temperature, and a host of other tests. For materials level testing, we're going to test samples that are going to simulate the component and joint that's going to be used in the product, and evaluate and expose the material to the stressors and evaluate the changes in properties and performance and the signs of materials degradation, and understand what's happening to the materials, and then help use that information to select materials that can be used in the product. So there are pros and cons for doing product testing versus materials testing. So for product testing, the pros of doing just product testing is that it's closer to the application, the real application, and the things that the components and joints will be exposed to. Can sometimes uncover unanticipated interactions and responses that brainstorming doesn't uncover. And it's less expensive. Well, there's a caveat to this. It can be less expensive than doing the materials testing, because there's extra cost in doing all this work. But this assumes that you pass the test the first time. Because if you don't pass testing the first time, and you have to do repeated tests over and over again, and also have to use outside agencies for repeated testing, then this can get really expensive. The cons are you need a complete assembly, so you've got to wait till you've got a prototype to test, and risks of delays and added expenses if failures occur during testing. The benefits of materials level testing are generating data earlier, so you get faster design decisions. You can test multiple designs at one time, test different materials and different forms. And you can also generate a design data library for coming up with design rules. But the cons are it requires extra cost in terms of the people, to do the testing and the equipment to do the testing. So I'm going to focus on discussing materials level testing. So with materials level testing, we can fabricate test specimens from stock materials or from other components that are similar to the components that were of interest. But we want to have the materials be the same as intended. And so this can have stock materials, components, can also consider coated materials, and also material weld joints or solder joints or adhesive joints that are made up specifically for the testing. And the other thing that I don't have on here is also just having test vehicles that are used for evaluation, that are used for common evaluation. So a test vehicle would be a standard test setup that's used for evaluating different materials for specific components or joints. So I know that in the like in the circuit board industry, and for people that are in the electronics industry, that people will have a circuit board test vehicles for evaluating the reliability of circuit boards from different vendors, and also evaluating the reliability of solder pastes or new solder paste and solder pastes from different vendors. And the same thing is also true for electronic components. There could be a test vehicle for that as well. But in any case, we're going to make samples that are representative of the samples that are going to be exposed to in the product without having to build the product. And then we're going to use accelerated stress testing to evaluate them. So it can take a long time to generate data using actual use conditions and usage rates. So we use accelerated testing to speed things up. And I know that reliability engineers are all familiar with this, but I didn't know who was going to be attending, so I'm including it all. So accelerated stress testing can be done in a couple different ways. It can increase the use rate. So instead of, so for some products that might be only used on and off, be turned on and off a few times a day, we can speed up the cycling, so use it a lot more frequently, so have faster on-off cycling or have constant exposure. And there's also overstress, so increasing the stressor severity. So examples are increasing the temperature, increasing the oxidant concentration, or increasing the electrical current. But what's important with increasing the stressor severity is that it's important to understand the effects of the accelerated conditions on the materials, because what we don't want to do is cause degradation or failure modes that don't correspond to normal use. Because if that happens, then we can end up causing failures that are not representative of what would happen in the product, and can end up excluding designs, because designs that would otherwise be suitable because of that. And then also we can combine these, increase the usage rate as well as increasing the stressor severity. So I have some examples of some different materials level testing that could be done to evaluate the response of materials to the exposure conditions. So in this example, we have, let's say we want to, the product has tubing that's going to be welded in the tubing or in the product. And we want to try using different steels, maybe a carbon steel, maybe a alloy steel, and also stainless steel. And we want to look at welded samples of those. We're going to make weld joints between the different materials and expose them to fatigue. So that the material is going to be exposed for some reason, the weld joint will be exposed to repeated cycling, repeated stress cycling. So we can make test samples and do fatigue tests on them, and we'll measure the number of cycles, the failure, and also the weld joint afterwards. And we can use a microscope, non-destructive testing, and tensile testing to evaluate how the material degraded during the testing. And the reason we might do this is because maybe we want the materials also exposed to a corrosive environment. And maybe carbon steel would be great to use, but because it's less expensive, whereas, but we might be concerned about the corrosion of that steel, and stainless steel might have the corrosion resistance we need, but it's more expensive than carbon steel. So we'd prefer not to use the stainless steel. So we might want to try the different materials with different weld joints and see what happens. And we can also try different coatings on the materials as well and see how those affect the weld joints. Then there's a non-stick coating for a cooking pan. So we have a cooking pan, they have non-stick coatings on them. The non-stick coatings are supposed to prevent food from sticking to them. Also, we would be great to have a non-stick coating that never scratches. And also want to have good adhesion between the coating and the metal that which it's being applied to. So but instead of having to make an entire skillet and test a large skillet, we can just get samples of the metal, let's say it's stainless steel or copper, and coat it with the desired coating, and we can do different coatings, and then expose it to wear, to scratching, to heat, and then to cycling between low and high temperatures, and then measure the adhesion of the coating to the metal, the amount of wear, the scratch depth, and also the non-stick behavior. And there's a number of different measurement techniques that can be used for this. And then if we have a plastic component that's going to be exposed to solvent materials, what we can do in this case is we can get dog bones made of the plastic material, and then soak it in solvent or expose it to the solvent or expose it to whatever else we're concerned about being degrading the material, and then have a sample already made for doing tensile testing to measure the material's strength and ductility. So we use a tensile test for that. And then also, of course, we can also evaluate the material, other aspects of the material afterwards to understand how the material is degraded. So this is a case where we've made a test sample that can be tested after exposure to the conditions. And I got two more. Well, this one is a tanker coating. This is the tankers sometimes carry liquids that are corrosive to the carbon steel that make up the tanker wall, so that there has to be a coating applied to the inside wall of the tanker. This shows the inside of a tanker where there was permeation of the coating by a chemical that's actually used in foods. It was a liquid food chemical, and that chemical is corrosive to carbon steel. And what happened is that chemical, or that food liquid, over time was able to permeate through the coating and start attacking the steel. You see, these are blisters under the this is blisters in the coating, where the rust that's being produced by the steel is pushing out against the coating. So we might look at the testing, rather than building an entire tanker and filling it with the liquid. We can get test samples coated with the coatings, do different coatings, different thicknesses, do different temperatures, and understand and characterize the coating behavior over time. And finally, we can look at the wear resistance of materials by doing wear testing. You do different alloys, different heat treatments, and different coatings, and evaluate how the materials wear during the testing. So we have rather than having to build an entire bucket or an entire huge piece of equipment, we can do individual testing, individual materials testing, get lots of data, and have very informed decisions when selecting materials for our products. So that is it. I've taken up the entire 45 minutes. So I hope that was informative to you. Are there any questions? And hopefully I have answers for them. So someone asked the question earlier, by material level, do you mean part or component level? And exactly, I mean material level from on the component or part level, or joint level for that matter. Well, Fred, it doesn't look like there's any questions.
Yeah, that happens sometimes. It's when you cover a lot of information, there's, it's,
Yes, yes, a high level view of all these different topics.
yeah. And it's, I've been talking about, kind of listing failure mechanisms just in general with definitions behind it. So this is rich material for me. I've been taking notes. So I think Andre's mentioning something here. If you see that in the chat.
So someone says, okay, you mentioned tensile stress as a necessary condition for fatigue. What about pure shear stress? As long, so I'm not a mechanical engineer, but as long as the stress has some tensile component to it, then that tensile component can be the cause of a fatigue crack. But there has to be a tensile component on a tensile component of the stress on the thing that's being stressed. That is one of the requirements for fatigue.
Michael, don't you? I'm thinking of images of bolts that have been broken, and there's usually both aspects, right? There's a part of it has got the tensile where it's deforming, and then it breaks and it just shatters. And I don't remember the technical words.
Well, right. So you have, that's what I explained during the fatigue part. It's you have the crack, the fatigue crack forms and grows, and it's growing at stresses that are lower than the metal's nominal yield strength. So we don't see deformation of the material, or we don't see we don't see macroplastic deformation. There might be striations, and then when the stress gets large enough, the remaining intact material can fail all at one time. So the crack shoots through the remaining material, and that's when, yeah, and then the failure occurs. Well, that's when you see the part suddenly stops. But the fatigue crack can be growing. The length of the crack of a fatigue crack that a material can tolerate before you get the fast fracture depends on the material. It's called on its fracture toughness, and also how, yeah. So the higher the fracture toughness of the material, the longer a crack it can support before it fails. Right. So someone says, so in solder fatigue, what it says shear stress is usually the key contributor to the solder cracking. There is shear stresses, but there still has to be the fatigue in the end, there's still going to be a tensile component that's going to be causing the crack to form and grow.
Well, from my understanding, to try to address Andre's deal, and I'm sure you're familiar about it, is, the thermal cycling creates that shear stress. And
yes,
it's actually not just pure shear, it goes in all kinds of directions.
Exactly.
But then as the solder relaxes under that stress, it starts to create molecular level or crystal level damage. And lead solder we had pretty well characterized. A lot of the new solders we're still working on, but it's a a change in the solder bulk itself that leads to the ability for it to crack. It's changing that material property so that it becomes, in a sense, more brittle. And
Yeah.
then a crack starts.
Yeah.
And then the continued cycling then take it apart.
And
But
you see the
it's-
same, yeah, and you see the same things. Well, for even for a metal bar, there are things going on a microscopic level that even in a totally smooth bar that can lead to the formation of a crack. So there's degradation. Degradation is the wrong word. There are changes that are occurring on a microscopic level, even in a smooth bar, that enable a crack to form.
And Gary's got an interesting comment here to catch one more question here is do we include stress relief factors in the testing? And, I've got an opinion on that. What do you think, Michael?
Well, certainly, Gary, are you referring to whether someone does or does not do stress relief on a component?
Well, yeah, I think that's, maybe the design has got a stress relief.
Yes, okay.
Yeah.
Absolutely, because so residual stress in a component can contribute to fatigue, or can reduce the fatigue life of a material. And so evaluating a material with and without a stress relief might be important to understand the differences. If you have a component and we're concerned that we might have to do stress relief, I would want to know, do we need it or not, before spending the money on the stress relief. So doing evaluations on a material that's been stress relief and hasn't been stress relief might be informative in order to make that design decision. And if it's someone who just says, I don't care, I just want to get rid of all the stresses, then they're just going to do stress relief regardless. But certainly that's something to take, that's a variable to take into account when designing tests.
Yeah, no, I see Brian's comment here on this one. I've also seen somebody said, well, we think this is going to be a problem, so we're going to put stress relief on it. And it happened to be something that we were going to test anyway. And the stress relief made it worse. Without the device they put on there to do the stress relief, think of like a cable, it actually made it much, much worse. And it was like, all right.
Yeah. So I think, so Gary, I think, so I was assuming you were referring to stress relief heat condition, or heat treating, or a heat treatment used for stress.
There you go. You're just a metals guy. I tell you.
Yeah, that's right. I'm just a metals guy. I wasn't thinking about stress relief for electronics. Now, once you said that, I realized that.
Or even undercoating, when you underfill a component, sometimes that, if it's not done well, can cause problems. And
there's always unintended.
Looks like we got another question there. Who's got Brian?
Yeah, there's always unintended consequences. There can be unintended consequences for engineering, for things we do, and they have to be thought out to make sure that that whatever improvement someone puts in place doesn't actually cause more problems than it solves.
Oh yeah, and Brian's on that same thought. Is it could have that consequence, a variable effect in production environment. Yeah, it adds more noise to the response for, say, a cutting machine, for example, or some other device. Yeah, no, well said. All right, cool. Well, I think we're getting close to the end there. Yeah, inconsistent heat treat. Yeah, that would be a problem.
Oh, absolutely, yes, and that part of. So that's a whole other discussion. I think I wrote it. Fred, you did a discussion about it, and I wrote an article about it. Is part of reliability is selecting good suppliers, because you select suppliers that can't control their processes, then
you get a wide range of results,
wide range of reliability, a wide range of components with different capabilities. Yeah. All right. Well, I think that's it. Well, thanks for letting me do this webinar, Fred. Everyone, thanks for attending.